So have you ever seen a Formula One car stuck in traffic going 20 miles per hour? Sounds funny, right? This car is designed to go 200 miles per hour, but it's just crawling. That's exactly what's happening with your GPU when you run LLM inference. You have this powerful GPU, maybe A100, maybe H100, thousands of cores, can do trillions of calculations. But when you run your LLM, it's crawling. Why is that? So for years, the industry said bigger is better. More parameters, more GPUs, more batching, just keep scaling. But here's what happens. At some point, you scale up and nothing improves. You hit a wall. And that wall, it's not compute. Your GPU has plenty of compute power. The wall is memory, specifically how fast you can move data around. Today, we are going to understand why this happens and what we can do about it. Now, one important thing, if you're preparing for the NCP-GENL certification, pay attention. This content covers 40% of your exam. Model optimization is 17%, GPU acceleration is 14%, deployment is 9%. So expect questions on these topics. Let's get started. So let me explain how people used to think about this. You have one user request coming in. That single request uses maybe 1% of your GPU. All those thousands of cores are just sitting there doing nothing. So what's the obvious solution? Batch them together. If one request uses 1%, batch 100 requests. Now you're using 100%. Simple, right? This worked for years. Training, batching works great. Image processing works great. Traditional ML works great. The goal was to make your workload compute bound. What does that mean? It means the calculation speed is your bottleneck. Your chip is working as fast as it can. That's what you want. But here's the problem. LLM inference doesn't work this way. No matter how much you batch, it stays memory bound. The bottleneck is not calculation, it's data movement. And that changes everything. So look at this chart. This is very important. On the left, we have throughput, tokens per second. On the bottom, batch size. On the right, latency, how long users wait. Now see what happens when you increase batch size. Batch 1, 2, 4, 8. Throughput goes up. Good, the strategy is working. But then you hit this point, we call it the knee point, and throughput just stops. Batch 16, 32, 64, 128, no improvement, flat line. But look at latency. It keeps going up. Users are waiting longer and longer. So think about what's happening past this knee point. You're using more memory. You're burning more power. Users are waiting longer. And you're getting zero extra throughput. You're wasting resources. The old playbook is actually hurting you here. So why is this happening? Let's look at that. So here's the uncomfortable truth. Your GPU is mostly just waiting for data. When researchers profiled Llama 2 and OPT models, they found that over 50% of the time in attention kernels, the GPU is stalled. Not calculating, just waiting for data to arrive from memory. Think about that. Half the time, your expensive GPU is doing nothing. So look at this analogy on the slide. On the left, we have compute bound. Think of it like a slow chef. The chef can only cook so fast. Orders are piling up. Solution? Give more orders, batch them, hire more chefs. On the right, we have memory bound. Now the chef is fast, very fast. But the delivery truck bringing ingredients, it can only carry one bag of onions at a time. Doesn't matter how many orders you give the chef, everyone is waiting for that slow truck. That truck is your memory bandwidth, the highway between GPU memory and the processing cores. In LLM inference, your chef is fast, but your truck is slow. This is called DRAM bandwidth saturation. The highway is full. No more data can flow through. Adding more work doesn't help because the highway is already maxed out. So why is LLM inference memory bound? There's a technical reason. There's something called arithmetic intensity. Simply put, how many calculations do you get per byte of data you move? High is good, low is bad. For normal matrix multiplication, arithmetic intensity is high. You load data once, you do lots of calculations on it. That's why batching helps. More batch, more calculations per data load. But LLM attention is different. There's something called KV cache. And here's the problem. This cache grows when you increase batch size and when conversation gets longer. Look at this formula. Cache size equals batch times sequence times layers times heads times head dimension times precision. Let me break this down. Batch. Each user needs their own cache. Sequence. Each token in conversation adds to cache. Layers. Every transformer layer has its own cache. Heads and head dimension. Each attention head stores keys and values. Precision. 16-bit means 2 bytes per number. So let's say 10 users, 1,000 tokens each, 32 layers, 32 heads, 128 dimensions, 2 bytes. That's gigabytes of cache that needs to move through memory bandwidth constantly. Here's the key insight. When you double your batch, you also double your cache. The ratio stays the same. You can't escape the bandwidth ceiling by batching harder. So if batching doesn't solve it, what does? We need to attack this at 3 levels. Think of these as 3 pillars. Pillar 1, the engine. Start with optimized runtime like TensorRT LLM. These have pre-optimized kernels. Don't try to build this yourself. Pillar 2, the weights. Compress your model parameters. Smaller model means less data to move through bandwidth. Pillar 3, the memory. Actively manage your KV cache. Compress it, throw out old entries, move inactive parts to cheaper storage. You need all 3. One alone won't save you. Let me show you each one. So batching isn't useless. You just need to do it smartly. Step 1. Find your knee point. There's a tool called Batching Configuration Advisor, BCA. It finds the optimal batch size where you get maximum throughput without wasting resources. Step 2. Once you know optimal batch size, you realize you were over-allocating memory before. That freed memory, that's gold. Step 3. Use that freed memory to run multiple model replicas. Instead of one instance with bloated batch, run 2 or 3 instances, each at optimal batch. This gave 33.7% throughput increase on OPT 1.3b model. The idea is stop packing everything into one instance. Start parallelizing across instances. So a 7 billion parameter model at 16-bit precision is about 14 gigabytes. Every time you generate a token, that 14 gigabyte needs to move through memory bandwidth. That's the problem. AWQ, activation-aware weight quantization, shrinks this. Here's what the researchers found. Not all weights are equal. About 1% of weights are critical. These connect to high activation neurons. They carry most of the model's intelligence. The other 99%, less sensitive. So AWQ does this. It identifies that critical 1% by watching activation patterns, protects those, compresses everything else to 4-bit. W4A16 means W4 weights are 4-bit instead of 16. A16 activations stay 16-bit for accuracy. Result: model shrinks almost 4 times. Less data to move, same accuracy because important weights are protected. The code is just 3 lines. You can see it on slide. So once you compress weights, guess what becomes the biggest memory consumer? The KV cache. And remember, this cache grows with every token, every user. At scale, it can be bigger than the model itself. 2 strategies. Compression, make the cache smaller. Keep it on GPU. Offloading, move inactive cache to CPU, RAM, or disk. Let's look at specific techniques. So researchers found something interesting. Attention scores follow a power law. A small number of tokens, they call them heavy hitters, get most of the attention. The rest, almost nobody looks at them. H2O tracks which tokens get high attention over time, keeps those heavy hitters plus recent tokens, throws away everything else. Result? Up to 5 times throughput, keeping only 20% of cache. 80% of tokens can be safely thrown away. Quantization, KV quant, KIVI. Same idea as weight quantization, but for cache. Store cache entries in 8-bit or 4-bit instead of 16-bit. Gives 2.3 to 3.4 times improvement. Attention compression, squeeze attention. This changes how attention works to need less storage. Gives 1.7 to 2.8 times improvement. Offloading. User is typing slowly, taking a break. Their cache is sitting in expensive GPU VRAM doing nothing. Offloading moves inactive caches to CPU RAM. When user comes back, reload it. The key thing, transfer cost must be cheaper than recomputing the cache from scratch. Peak performance isn't achieved by guessing. It requires a systematic, iterative process of measurement and optimization. Here's the cycle. 1. Profile. Capture a detailed trace with NSY's profile. 2. Analyze. Use NVIDIA Nsight Systems to identify the true bottlenecks. 3. Optimize. Apply a targeted technique from the 3-pillar framework. 4. Build and deploy. Rebuild the engine and push to production. Then repeat. You cannot make these decisions on intuition. You must see the system physics in action. Every time you fix one bottleneck, you reveal the next one. So the efficiency cliff is real. Your GPU is probably 50% idle right now. But now you understand why. Memory bandwidth saturation, low arithmetic intensity. You have a framework, engine, weights, memory. You have tools, Nsight Systems. The future belongs to those who understand the physics beneath the code. Go build something fast.